In the molecule shown below, which hydrogen atom is the most acidic? So what we've talked about previously in terms of determining acidity based on structure is that we have this general trend in terms of things we should consider. So charge would be the first thing. If you were to see a hydrogen attached to an atom with a positive charge, you should think of that as most likely being acidic. The atom that the hydrogen, and we don't have any charges, so we don't need to consider that in this case, the atom that the hydrogen is attached to. So the two things that we saw for atom that we had to consider was the size of the atom and the electronegativity. All of these hydrogens that are indicated here are attached to carbon, so that is not a factor we need to look at. So we're going to keep moving down the list, and we'll get to R, which is resonance. And since we have carbonyls in this molecule, we have the possibility of resonance stabilization if we remove one of the hydrogens that's alpha to the carbonyl. So resonance is going to be important here. That's what we're going to be looking at as our main factor. So with that, we should immediately eliminate A and B because these do not have resonance stabilization. They are not alpha to the carbonyl. So with no resonance stabilization, these are going to be about as acidic as a regular sp3 carbon hydrogen, which when we think about the acidity of a normal sp3 carbon hydrogen in like an alkane, we're looking at a pKa of greater than 60. So that's not acidic at all. So we are not going to be considering those. So that leaves us with this one that's labeled HC and the one that's labeled HD. And so with these hydrogen C sandwiched in between these two carbonyls, you've got extra resonance stabilization. So when you remove this hydrogen, you've got resonance stabilization with both of those carbonyls. Versus with D, you have the resonance stabilization with just one carbonyl. So D here, being alpha to a ketone, has a pKa of approximately 20. And C here, that's sandwiched between that ester and that ketone, has a pKa of approximately 10. So this is definitely our most acidic hydrogen. And I want to just take a look at the resonance stabilization that we see here. So I'm going to redraw this initial structure. So we've got this ethyl group, oxygen, we've got our carbonyl of our ester, and then we've got the other ketone with that CH3. So if we've removed this hydrogen C, so let's imagine we removed it, then we have this negative charge. And so we can resonance stabilize this with the ketone. So we can share it with the oxygen of the ketone carbonyl. So we see this. Resonance. And then we can also push these electrons back through to the ester carbonyl as well. So it's this extra resonance stabilization that I'm drawing here that is making the, I drew that bond where it shouldn't be. Let me quickly get rid of that, right? Because we moved those electrons up onto the oxygen, so they should not have been there. So if we moved it, this double bond here, we need a double bond right there. We put extra electrons onto that oxygen, so that has the negative charge. And then we have our other carbonyl. So we reformed the carbonyl there. So in looking at these resonance structures, it means that that negative charge is shared with the carbon and both carbonyl oxygens. So that's what makes it so much more acidic than even these hydrogens that are alpha to the ketone.